Just a clarification on the website. It says that I'm from aerospace and defence side of Airbus. I'm actually from the commercial aircraft side. So what I'm going to be talking about is the commercial aircraft aspects of it. So I'm going to spend some time just introducing what we do, then how we go about using uncertainty quantification for the conceptual phase of the aircraft, actually making some ideas about how we're going to go forward on those. And then a little teaser about where the difficulty arises. The case study I'm using, I hope, is one that works across all the different disciplines and all the different industry sectors that we have here, so I'll introduce that to you shortly as well. So we already heard some of the reasons why we want to use uncertainty quantification. I mean, for us, the main thing here is that we do have constrained timescales, we have constrained budgets. We're always looking to be one better than the competitor. At the moment, it is one competitor. Who knows, 2 years' time there may be more, so we'll have to speed up even more. But in order to do that, we want to be able to learn as much as we can earlier. And we feel that UQ, uncertainty quantification, is one technique that not only helps us to understand where the uncertainties lie, but also to help us learn about what the product might do as it comes into realization. So what I've done here is to just highlight the external influences in red and the internal things we're doing in green. And just want to make a quick mention about the topic we're talking about in terms of sharing information. You're right, it quite often is human beings who are dealing with sharing the information and working around the data. But what's imperative is to know what is the assumptions that are in the data itself. So the key part here about communicating margins is one way of making that explicit, because if we leave that implicit, then we don't actually know what has been done in the past, what margins have been applied, what uncertainty has been taken care of, and we may find that we're over adding the margins all the way through. And one of the things we want to do is to be able to then come up with some appropriate ideas of what the uncertainty is in the data we have in real terms, as opposed to it just compounded over and over again. So those are the things that we want to be able to look at. Why do we want to use uncertainty? Well, we don't actually know what the future is going to give us, especially when we're looking at new technologies. So we want to be able to look at the value of embedding those new technologies into our products and what benefits that they might give us in terms of performance of the vehicle, in terms of the viability to buy the vehicle and operate the vehicle and so on. And we also want to be looking at new manufacturing techniques that we may not actually have background information on, because they are that new that we don't have enough historical information to be able to make some judgments about those. So those become areas where there is the unknown side, which will become known as we approach it more and more. So this is what we're referring to as epistemic uncertainty. And then there are those parts where the new technologies will still have their variability associated with them, and we need to be able to take into account what those variabilities are going to be. And the key thing here at the top is that in the early stages, when we've decided what the product is going to be, we've already committed to 80% of the cost of the product. So if we're making sure that we've committed that in the right 80% in the right direction, then of course we're going to end up with a product that we actually want and the market wants as well. So we're also looking to project those things forward as well. So this is taken from a management slide, so bear with me, there are some very basic ideas here. But the key thing we want to try and put across is that uncertainty quantification is more about the probabilistic approach. And we also use the term management, EQ and M. Management is about having got that information, what do we do with it? And this is quite a difficult question, because how do you communicate some analysis has taken place and uses statistical language to a bunch of decision makers who may not necessarily be engineers? And getting that information across that wider group, but backed up by the right level of information, is quite a critical thing for us to do. So the management here is, having done all this analysis, so what? What do we need to be able to do with that analysis? And it's a critical part we've been looking at as well. We've been working with a couple of key partners you see there, University of Bristol, Liverpool, Imperial College, and across the ocean to ASDL at Georgia Tech as well. And in terms of the application areas, we know that we've got Lockheed Martin, we know we've got Rolls-Royce working on this, we've just seen the results of those. And of course a competitor also are using these techniques too. So within the aerospace industries, it is a growing field. And I think it's an important one here from Professor John Ockenden. At the last study group for uncertainty quantification, did make a statement that uncertainty quantification is one of the key topics that we need to be looking at from industrial mathematics side. And I think it's the sort of presentation that Catherine gave earlier as well that indicated how that is going to be used. So the thing I'm feeling a bit guilty about is the simplistic middle bit there about what this actually means. So I'll skip over that. So when it comes to the types of models we're using, where complexity arises is that we have got some situations, as Alex pointed out, where we've got fully coupled set of models. And that means that it's been operated on by a group of people who are already interacting and talking together. Now that's useful because they're able to share the uncertainty they have, they're able to do the calculations that they need to do, and that uncertainty can go in as a set of inputs. All the internal uncertainties are also being declared as probability density functions, and we can produce an output that indicates what the output of that set of models is actually going to provide us. But we also have loosely coupled ones, where quite often these uncertainties in the figures that are produced by each of the domains are not actually shared, they're implied, they're referred to as reserve factors. What we want to try and do is to open those up as well, so we can see, does the uncertainty from a previous calculation set encompass the uncertainty that I already have, or do I need to be adding some margins onto to my work as well? But we also work across the extended enterprise, and that means that we've got information coming through which isn't in any way coupled together and may not even be consistent. So we need to make those things consistent and somehow enable us to do some studies around those areas as well. So I think this is quite an important area that sort of touches on the back end of the conversation that we had with Alex, is that we need to be able to take into account the way the data is shared and somehow maintain the provenance and pedigree of that data so as we know where it came from, where it's going to be going to, and how we should be using it. And that's the metadata that's actually quite important to impose on top of the data to enable us to use it in some sort of a realistic form in the work we want to be able to do. So I mentioned that we're going to talk a little bit about overall what we do. So I've got this as a cartoon which we'll bring through here. It's about the conceptual design, and in the conceptual design phases what we're looking to do is identify a set of products that meet a specific market need. This need may not be expressed as a requirement, not hard and fast. It may be linguistic and vague in the way that it's expressed, but there will be some expectations behind it, and there will be some values that are being sought by it as well. So this then creates for us a product placement scenario. This is what we would like to be able to put in the market to go into place in, say, 10 years' time. So what we can do with that is start thinking about some of the concepts in terms of what the aircraft might look like. But we also have a portfolio of technologies that we're working with, and we'll talk to our friends at Rolls-Royce and say, what sort of engines have you got in mind, and how can we use those engines on our aircraft as well? And there will be uncertainties associated with that, as we heard earlier. And there's also a future operations always taking place in terms of how it's going to be operated. By operations here, I'm meaning much wider. I'm thinking about not only how the airlines will fly the aircraft, what the air traffic control environment might be, but how we might support the aircraft, how we might maintain the aircraft, how we might produce the aircraft. So the different concepts are coming through here. And if we were to take a sum of all those, then we can end up with a large number of aircraft concepts that we can start analyzing in that multidisciplinary way. So just showing that as a set of axes here, what we've got now is that each blob there represents a individual aircraft that has a specific technology embedded in it, a specific way of maintaining it, and a specific shape associated with it. And what we want to be able to do is to use some rapid methods to say which ones are not feasible. So we're not going to make a selection and say this is the aircraft we want to design. What we're going to say is these are the aircraft we don't want to design. And in the literature this is known as set-based current design or set-based design. And the idea behind this is that you always leave yourself a number of scenarios that are still feasible by only getting rid of the ones that are unfeasible. The danger of picking one and finding later on that it doesn't quite work is wasted effort, and you have to come back and redesign, so it can be a costly task. And from those we can then create a set of feasible solutions, and because we've narrowed the set from a very large one to a smaller one, we can increase the depth of calculations necessary on this, and we can go into deeper calculations as Catherine showed with the finite element approach, computational fluid dynamics and those sort of models associated with it. And from that we can then come up with a feasible set of competitive products that we want to use. Now what I want to do is just take a a case study of how we apply this by looking at the rapid methods part, looking at the early design and being able to pick out a large number of engine configurations and a large number of airframe configurations and show how we're using these methods to home in on what are suitable and feasible solutions that might come out of that. I also want to touch a little bit on the graphics that we produced to be able to show what this means and how we might use these things as part of decision making. So the simple case study we're going to look at is an aircraft that's taking off, going into transition phase, reaching climb and then going into a cruise environment. And one of the things we want to try and do is to ensure that the aircraft can fly 24/7. Now essentially what that means is that we want to reduce noise. Because we want to operate it on a regular basis, we also want to reduce the emissions from it, and we want to be able to reduce the fuel burn associated with this as well. So the terminology you'll see is SL noise for side level noise, FO for flyover noise, and fuel burn and NOx will just come through as emissions. So there are some specific areas where these noises are measured. So there are microphones. I'll just show a picture at the top there indicating some of the microphones that are positioned at the end of runways to measure these noise. And what we want to do is create a set of possible aircraft designs. So here we're talking about combinations of just engines and airframes without going into any detail to what the systems might be. And using those 4 items that are marked in blue there as our figures of merits, what we want to try and find is the best solutions that meet all those criteria. And use those to be able to narrow down those configurations of aircraft and engine that actually meet all of those criteria. So to do that, first thing is that we generate the data. Arcadia is a computational tool or a framework from Cranfield University. We used that, and we also used a tool called P7, which is allows you to do surrogate model build, and it's got a number of ways of being able to build surrogate models, and it includes Gaussian processes as well, and we use Gaussian processes in here. Now what we've done here is to separate out our design parameters from our random parameters. The reason for this is that we want to treat them in a different way when we come to do the full analysis. Design parameters are parameters we can choose. Yes, there are tolerances associated with them, but those tolerances are much less than the uncertainty we have in the random parameters. And those random parameters are giving some indications to what that future technology might provide us. So if we have a figure of 1 associated with that design efficiency, then it means that it's the same category as it is now. If it's less than 1, it means it's getting worse. If it's greater than 1, it means that the technology is going to offer us more. So we're able to then take lower and upper bounds, and again using design of experiments, make some selections, run it through the Arcadia tool as a simulator to generate a set of points. And then we can use those points to generate a surrogate model, and from that surrogate model then be able to do a lot more runs and essentially do thousands of runs. So we're treating the work that is produced, the data that's produced by Arcadia, as being a computationally expensive set, even though Arcadia isn't, as a means of being able to generate the data and make the separation. And again, as we saw earlier, what we want to be able to do is then see how good is that model. So at the top there you see, well, I'm comparing the outputs of the Arcadia model with the output of my surrogate model, and if they are on a straight line, then I've got a very good fit. So we're looking to see how good that is. So we're checking for linearity of that in the first plot there. We also want to make sure that the behavior that we get from our emulator is close to the behavior of the simulator in terms of what the probability density plots look like as well. So we're able to check those as well, and come up with a series of error estimates. So there are a number of ways of being able to measure that. We've got over here root mean square, relative root mean square, maximum minimums, and quantiles of 90% and 95% and so on. So that enables us to see how good is the surrogate model compared to the simulator that we use to generate the data with. And these things are typically used by the analyst, not so much, I suppose, exposed to the decision makers, because it's a level of information they don't need to know. What they need to know is that we as analysts have confidence in the information we produce. However, we do keep this in our back pocket, so if they do need to know, well, what is your confidence based on, then we can pull these things up. Now, what can we do once we've got this? And there are a number of schemes we've been looking at to display the results. First thing I want to point out, let's start over here, and we'll work our way over to the left-hand side. We don't actually know what the probability density function is going to be for a given set of technical characteristics of the aircraft or the airframe or the engine. It could be biased one way, or it could be biased another way. So what we want to be able to do is to run different scenarios considering these different types of distributions we might have. And I'll just give two examples here. We ran through quite a few. For each of those examples, what we want to do is be sure that we're below the margin that's been set for each of these characteristics. So here, the probability that nitrogen dioxide is less than 500 kilograms, I think, per flight hour is 70%. Whilst in the one above, we've got for that sort of distribution, we don't actually make more than 30% on that. We're much less than 30% probability of success of being below that margin. Now, that's useful because that allows us to now consider which ones of these technologies are ones that are going to give us a robust solution against these different figures of merits. And I just give you one as an example here. We'll come back to the others in a second. The other thing we can do is we can plot those along the anti-diagonal. Below we've just got the cumulative frequency distribution associated with the two elements we're looking at, and on the upper diagonal here, upper triangle here, what we see is the correlation between those figures of merits. The reason why we want to be able to look at the correlation comes back to what we were saying earlier. We're treating them as independent. They may not be independent. For example, nitrogen dioxide emissions are not independent of fuel burn. We didn't take that into account because we wanted to be able to see how the methods would work and whether we can spot those as well. Unfortunately, in this data set, it's not easy to spot, but that's where the engineering know-how comes in, is that they must be related somehow, so something's not quite right in the model. But these plots allow us to, I think more importantly, this type of plot allows us to convert the probability of success, if you like, against each of the figures of merits to a numerical value that we can then start to combine together. And the way we did this was to look at each one, and here again I'll give one example of the situation that we've got for block fuel, that we've got a particular engine airframe combination that doesn't meet the red line. The probability of success is actually quite low because we're majority of the time burning more than we should be. With nitrogen emissions, it's not too bad, and with flyover noise, we're not quite getting there, and certainly with sideline noise, we are, because all of that is well within the limit that we impose ourselves. And against each one, we've got, although it's not so clear, the area that's highlighted in blue in all those areas. And that's giving me the probability that I'm going to be below that figure. So with that probability, what can I do? This is the graphic we came up to be able to explain how we can combine a number of different figures of merits and their relative values together to produce the airframe one. So what you see here, each block here represents an airframe, so we've got 9 of those, and each vertical square represents an engine. And there are 81 of those, so quite a large number of selections of products that we've got here. What we're trying to do with the first one here is to look at those areas and color code them, and I know that blue and green should never be seen, but this color code is not necessarily a good one. But the blues are indicating that we're not meeting the criteria. The area in the blue curve is always a smaller one, or 0. The green, on the other hand, show that we are in a good position, and all of the peaks of those curves are to the left-hand side of those limit lines. So we can do that for flyover noise, we can do that with sideline noise, we can do that for emissions, and we can do that for fuel burn. Now, what's interesting is we wanted to come up with what are the aircraft's engine pairs that allow us to pick on the ones that are good. So we can multiply those now. Assuming equal weight, I can multiply those together, take the geometric mean, and plot them as an aircraft and engine combination. So this is now telling me the amalgamation of all this information set in one plot. So here we can start looking at areas which are green and areas which are blue, and we can ignore the blue ones, and some interesting things come out. For example, if we look at that particular row here, it means that an engine can serve a number of different airframes. So that might be something that Rolls-Royce are quite interested in, because they can now use the same engine for a number of aircraft that we might want to put out there. Similarly, if we look at some of the areas where you've got greens coming through on a column, that means that we've got an airframe that can take a number of engines. So if we think about the A320 as an example, within Europe it flies half hour to maybe 2 hours maximum. In the States it's going from coast to coast, and that's 4 hours. So we may want to change the engine depending on the mission, but keep the airframe the same. So this allows us to play those sort of games and look at the probability of success that the aircraft would meet those constraints if we were to put those there. So what I want to do now is just leave you with a taster of where this could take us. So that was a simple example because it's an early stage and we wanted to show how even at the conceptual stages we can use these techniques. This is a more difficult one where we're trying to set up the loads for a design of a new slat. Slat is the part of the movable at the front of the wing that changes the aerodynamic capability and therefore the lift capability of the aircraft. To design that, we've got a couple of examples here in terms of what the design sensitivities need to be. How deep is the manufacturing of the wing box that's going to be taking the load, the majority of load that's generated by the lift? The wings bend and deflect. It is a mechanical aspect, so how much do we allow it to bend? We've got structural interfaces as well. We've got kinematics limits to where it can move and where it can't move, and if the wing is swept back, how it's going to move and still give you the aerodynamic aspects. A lot of these now require a lot more processing power. So it's along the lines of what Alexander was saying, is that to combine these several characteristics together does mean that we've got very high computational powers needed and can take up to a week or two, or in some cases just prepare the models up to a month to make those runs and to get the figures out. So that's really where we're going to next with the application of uncertainty. And I just want to end very quickly on what some of the challenges are. After all, the presentation was about challenges as well. Problem formulation is always a key problem. It's not about the linguistic formulation, but it's about what is the mathematical problem that we're actually looking to solve and what would constitute a good answer to it. Decision theoretics is another one. Is having got that information, how do we then convert that to a narrative that enables the decision makers to feel comfortable about the sort of decision they need to make about the product? We already talked about modeling parametric uncertainties. Hierarchical models of UQ, I think, is something we just discussed as well, is how do you take that into account? The inverse problem, I was very heartened, Peter, this morning to actually make that link, which I hadn't done before, of how do you allocate those uncertainties to the right areas, some of which may not be controllable. So if you're able to spot that in terms of what the inverse solutions might be, becomes a very valuable way of working for us. Sources of uncertainties, we mentioned some, but there are others that we perhaps haven't discovered yet. We do have a high dimensionality problem. As we get deeper and deeper into the aircraft design process, we have more and more degrees of freedom, and those degrees of freedom create those high dimensionality problems. We do, as was mentioned earlier, have incomplete and noisy data sets to deal with, and large volume, and by big data here I mean looking at it from a perspective of how does one analyze disparate sets of data as opposed to necessarily the volume of data. Strategies of when surrogates don't work, so this is something that we still need to look at, and what do we do about it in order to get us there. And lastly, analysis to narratives. I think this is the sort of thing models of decision is covering as well. And I did have a chat with Professor Bowman as well about how we visualize this information set. So this is something that we're looking forward to meeting up with. So that's, I'll just leave you with information that you've already seen as overall conclusions of some of the areas we're looking at. Thank you very much.
Do we have time for questions?
Question to both of you, really. You've kind of given a nice overview of how complex this whole modelling situation is. And you talked a bit about people having problems in communicating because they're working on an individual part of the problem. Is part of the problem education? Do you find that you are able to recruit graduates who have the skills to do this kind of stuff? Or do you have to train them on the job? Do you think that the way that we train students on mathematics degrees, statistics degrees, is enabling them to come and work in companies like yours to be able to help you with the kind of challenges that you've highlighted?
Shall I take that first? I think there are a number of things associated with that, and it's not easy to pinpoint one of those. One is that there's a historical track record. We are a regulated industry, and we have methods and tool sets and people trained to use those methods and tool sets to enable certification of the aircraft. So that makes it difficult to change the processes. When we do look to change the processes, then we've created a rod for our own back, because the people we go and recruit from are the traditional disciplines. So getting people, even if they are rightly trained in that arena, we may not really have written the job description correctly to enable that to happen. In terms of the training, I think those people that we do get with those trainings coming in do find themselves constrained straight away, because they're not able to have the freedom they needed to apply those new methods because of those historical aspects and the inertia it takes to change them. I think finally, one of the things we've been looking at is that perhaps we need some well-described courses that enables our traditional engineers to start thinking about some of these techniques. And that way they're able to explore some of the uncertainty quantification techniques that we could be applying. Quite often, part of the certification process is that there is a reserve factor or a factor of safety that's declared on us through the authorities, and we can't get away from that. What we'd like to be able to do is to have some rationale to why that's still relevant, or work with the authorities to say, how should we change this? Because having now got new materials and new ways of doing things, perhaps those reserve factors aren't valid anymore. So there are a number of different areas that I think we need to attack. Finally, on the last part on this one is also to do with how do people interact with data. Because they've got these sort of hard fixed reserve factors in their tools, quite often they don't even think about whether they're communicating the data with those reserve factors in there, and the people who are then using that data for their own processes don't actually know what those reserve factor means in terms of their own work. So we do find that we've got reserve factors on reserve factors on reserve factors, and perhaps there is an over-design taking place that could be simplified and made simple. Are those your experiences as well, Alex?
Pretty much the same from our side, yeah. So you have people, not a lot of people have that training, but then you constrain them right away, putting them in the old organization. So there's a lot of stuff we need to do to really enable the people to succeed, people who have that skill set. There's not an awful lot around which have that skill set too, to think about across these disciplines and act as an integrator. People like to be segmented: mechanical engineers, electrical engineers, mathematicians, statisticians, and this is really good to bring us all together.
Yeah, I mean, one of the other things you mentioned as well, talking about the decisions, the decisions that are made by senior engineers, senior design engineers, if they're demanding confidence intervals around information that they're getting, then that cascades down and puts the imperative on people. And then you ask the question about skills and competence. Are you have we trained you properly for this activity? And then that puts the right kind of pressure on the training of the engineers, the broader design and analysis engineers, to become skilled, to fulfill that requirement. So in a way, you could think about it as the imperative is to train more senior people first, and cascade it down.
At least
rather
introduce
than
them
train
to
new
the
graduates.
Yeah. The other thing I noticed over when I first started in the work environment, we used to do plots with error bars.
Yes.
And we don't see them anymore. You see plots coming off their tools, and this is deterministic. This must be right because it came out of my tool, and I've been using that for years. So we need to overcome some of those problems as well.
Exactly, and it's the same on paper. If you publish papers 20 years ago, you couldn't publish a paper without error bars.
Yeah.
Now they go just through without. All that stuff, I think, has been lost a little bit in the glamorous, let's say, computational world.
Mm-hmm.
Can I make a remark that comes back to the one I've already made? I was 10 years in particle physics, and error bars are the central theme every day, all the time. Now I come to a wide range of disciplines. It's my remark before was, do you have a platform to be able to do this stuff and I struggled a bit. So there's a connection there, and it's building the right thing so that we're enabled to do this.
Yes, kind of building an error bar, let's say, on a system level quantity would be pretty much impossible nowadays because the background structure is not there. But that's where we need to get to at some point. And working together with getting the right structures together. There's areas who do that, like you said, particle physics and so on. You need to do it, otherwise you're just lost. But we need to merge these two things, I think, and put them into the engineering side.
I think we've got a question.
So I was very interested in the set-based method, and obviously I've heard a lot about it from Iran. But it seems very close to real option theory. So in a number of other areas like drug design in pharmaceuticals, they carry together chemicals or molecules which are close to each other and hope that one will make them a billion pounds. Right? So are you using, and also I like to make a link with finance, of course, where option theory started. Is that theory well developed of having these complex options in different and complex situations?
Not in engineering in the same way. I think if we look back at the point where within engineering set-based design and set-based concurrent engineering came from, very much the Toyota principle, and that was more about having different chassis, engine, and internal options that you could do depending on the market you wanted to go with. What we've seen over the last 20, 30 years or so is the move back towards how can we have a number of different vehicles but being designed at an early stage without necessarily just thinking about how do we set up a customized vehicle at the end. So what are the options that we have available to us? Real option has been talked about, but I've not actually seen the real application of that in engineering yet. We very much would like to work with the biomedic and the medical areas because exactly the points you're making there is how do they deal with it, because they've also got a very large design space that they need to be looking at. Quite a lot of the behaviors, as we saw earlier in the example of the heart, is that there are a number of different things that might be contributing towards it. So how do they deal with that? And I think there's an awful lot we can learn from those groups as well, especially when we come to look at the decisions about whether a product is a good product or not. Traditionally, we've used the performance of the vehicle itself. But just because it's high performing doesn't necessarily mean it's going to be a good market seller as well. So you need to be able to somehow link that back with the marketplace as well and make that business decision too. And for those, something like a real options approach may be the way to be able to look at a number of different concepts, and they may be quite disparate concepts, include supersonic, for example, to blended wing, to all of these, the standard aircraft in the middle, using the same type of metric to be able to assess and evaluate the value of each of those.
I do know, I do know some recent work on district heating and power in cities where they look at with complicated networks. They look at different options for waste heat and dealing with that. So there is some theory of options in engineering.
I have a last question to both of you before we go for lunch. It seems that there has been a cultural shift in engineering in the last decades, in the sense that probabilistic methods are more and more spread, and it's not nice to see. But there is something which is difficult with UQ, is to do the quantification properly. So if you inject a distribution that is meaningless, then you will have a quantification of uncertainty that is meaningless as well. And in a sense, it's very difficult to assess. So what experience do you have in terms of validation, assessment? You has brought something to your companies in terms of robustness, in terms of being more effective and maybe reducing risks?
There are, so the example I showed there is an example that now is getting into the future projects area of Airbus. One of the things they're finding is that we don't know what some of the distributions are going to be, so how do we go about finding those? We've been working with Professor Hagen, who's key in a lot of these things, and his papers seem to be all over the place, on structured expert judgment. So there are a number of approaches we've been looking at. So one is the Shelf approach from Sheffield University. The other one is Roger Cook's structured expert judgment. There's also the Delphi methods and so on. What we're trying to do with that is at least create a dialogue with those people involved, the experts involved in those judgments, to think about what these variabilities are going to be. So how do we, without having to do big experiments, can we have a starting point that the experts in the field that we're looking at can then say, well, this is the sort of band and this is the likely density functions you're going to have associated with it. So that's the conversations that we want to start developing in more detail. There are difficulties in each of those methods, and that's why we haven't yet found one that is easy for us to apply. I mean, the problem with the Cook's method is you need to have some test cases that allow you to look at the believability of the expert. That's not so easy to do, because if you're asking test questions, and some of those test questions could easily be looked up at, I don't know, say Wikipedia or somewhere else along those lines, then that's not actually giving you the information that you need to develop that uncertainty input that you want to put into your set of equations. The shelf method also has some difficulties in that you could quite easily end up with group thinking, so that you've got these people and you don't let them out until they've come to some consensus, and it's a unanimous consensus. Could there be a strong voice that stops the others from expressing their viewpoints? And it may be that you just choose the right experts who are much more involved and much more engaging in that sense. But so there are things that are happening there. I'm not quite sure how we move forward.
What's your take on that?
Yeah, it's pretty much the same on our side. It's really depending on the inputs you put in the process, what outputs you get. The other topic which really becomes important is really good validation of your toolkit. And I think that's still a big area where the predictions coming out of the tools, how good are they with respect to reality, and you need to put a really rigorous process behind that too, because otherwise, if you add these all up in the system level models, it's just a random number you pick at the end, and you don't want to do that. So there's quite a bit of stuff going on in what's going on in Sandia nuclear industry in the US. No tests anymore, so they need to do thorough validation stuff. So, but you need to merge now the V and V bit with the UQ bit and then do that whole picture. Now that it's becoming kind of more and more in industry, now that link needs to happen.
Just another point on that one is one of the things, like we saw with the Gaussian processes, where you can get an idea of where your next experiment is going to be in the computational sense. We're thinking about using the same sort of thing, is how do you treat validation verification processes using simulations and validation verification processes in the past that use the physical device itself. And one of the things we're asking ourselves is, could we use the Gaussian process type idea to say, where is it that we need to do one experiment that informs us about where we should improve our models?
So there's one point I was very struck when you were saying about the problems with Delphi and the strong behaviour. This is the strong personality driving the answer of the group. I believe Alberto Franco up at Loughborough has done a lot of work in this, because they're actually filming groups, and you can see an opinion die because one of the senior people goes,
yeah,
and that's
yeah,
it.
yeah.
It won't be in the minutes,
Yes.
but that is when that idea of ridiculous, it can't be that.
And I don't think we're quite so hierarchical in the UK, but we are a multinational company, and there are, I won't say who, but there are certain areas where hierarchy matters. And if there's someone senior, then you'll find the junior people will not speak up until they're asked. Yeah.
Okay, thank you very much to the two speakers and to everybody, and have a good lunch.